Okay. I think some of you guys, if you do this, the questions might be out of order, but just follow along with me. Question 1 that I have here, it's the one where there is an inclined track on a table and you release the block of mass M from rest and it slides down the track. So here she is up there. She goes down this way, and here you can see all of this speed here is horizontal velocity. Sorry, I said speed. Okay, it definitely says all friction is negligible, so that's great. So that is eliminating outside forces or frictional forces. So the block leaves the track horizontally, right? Strikes the ground at a distance d. Which of the following statement is true? Select 2. Woohoo! Okay, so if the block is released from a height 2h1, the block will land a distance 2d away from the track. If a block's mass is increased to 2m, the block will land 2d away from the track. So the first one, A, you have to do some math for that. I'm going to skip that. The second one, B, we know that mass doesn't change. So here's what we know. We know that in order to land 2d away, that our horizontal speed, our horizontal velocity has to increase, right? It has to double. So let me just write that. Right? Because there is no horizontal acceleration once it leaves the table. And in order to go a distance, so because we would have x equals x naught plus v naught xt, and then 1/2 at squared, axt squared, that goes away to 0 because there is no acceleration. So basically, and this is 0, that also goes away. So basically our x, or our d, is equal to this speed here times t. Our t isn't going to change. T depends on, because this is projectile motion, T depends on our change in Y, right? So our change in Y is going to be equal to V naught Y T plus 1/2 A Y T squared. There is no V naught Y because it's all horizontal. So 2 times the change in Y divided by A Y, which is -10. We have a -2 for change in Y. Nope. Yeah, our change in Y is whatever. Hold on. Eraser. Let me get rid of that. Okay. -10 equals T squared. Our change in Y is going to be -h2, so we'll have 2h2 over 10 equals T squared. T equals square root of 2h2 over 10, or h2 over 5. Square root of h2 over 5, right? So if you move the table up, it'll go for longer. But the horizontal, so basically coming back here, the time stays the same if you release the block from a height of 2h1. The time still stays the same because the time is based on just the height of the table. So if the time stays the same, then this would have to double. It won't. This speed here is equal to 2gh1. If you double gh1, then you would have square root of 2h1, which gives me 4gh1. Square root of that would be 2 square root of gh1, which is not twice that square root of 2gh1. So this one is no. And then the other one, B, also no. Okay, so C and D better be right. Let's look. The total mechanical energy of the system containing only the block increases from the moment of release to the moment it strikes the ground. So only the block means no earth. So the only mechanical energy you can have if it's only a certain object would be kinetic. Okay, does the kinetic energy increase from the moment it releases to the moment it hits the ground? Yes, because the speed increases. So this, yes. The total mechanical energy of the block Earth system remains constant. So this is kinetic plus UG. Yes, because friction is negligible. So yes, that's true. Okay, that was a lot. We're going to go on to the next one. There we go. Okay, here we go. An object is released from rest above a motion detector so the data can be collected about its motion as it falls to the ground. Okay, experiment is conducted near the Earth's surface. All frictional forces are considered to be negligible unless otherwise stated. So something's in free fall, and then there's no friction. Great. So here's the kinetic energy. The student collects the data necessary to graph the object's kinetic energy as a function of time, which they show us. Which of the following graphs represents the sum of kinetic energy and gravitational potential energy of the object Earth system as a function of time? So we know that object Earth, great. That means that UG is included. Okay, and because they set up above, there's no frictional forces. There's basically no outside forces. All of the forces are included in the system because they included the Earth. So all we need to know is basically, if there's no outside forces, then energy is conserved. So our kinetic plus gravitational potential should be constant. There's no mention of any sort of spring involved here. So there's no EPE, there's no trampoline, none of that. So the answer is going to be A. This one's constant. You can see that. I'm not even going to talk about the other ones. Okay. All right, great. So here we go. We've got this conveyor belt going on here. Here's another one. So we've got, you can read this. It wants to know what happens for a system that only includes the object. Which of the following best describes what happens to the mechanical energy of the system, which is object, right? When the object is moving from the bottom to the top. So what it's telling you is this has a constant speed. So if it moves from the bottom to the top, there's only kinetic energy. If it's constant, that means that mechanical energy is constant, which is C. Okay, object increases, no. Decreases, no. And then no. So it's got to be C. Okie dokie. So this question, I'm assuming that you have already read it. I'm not going to read it to you. Basically, there's two objects, and it's telling us here's the kinetic energy of both at a time, from time t equals 0 to t equals 10. And they want to know, they talk about what's the GPE of the object Earth system from 0 to 10 seconds, or how much does it change? So there's two objects in the system, so we just add them up. We just say, well, the kinetic energy changed from 0 to 400 and then from 0 to 1,000. So 1,000 plus 400 is 1,400. So that's how much it changed. Fantastic. All right. And one more. And then I have to go to my win block and I'll finish the rest later. Shoot. Okay, so again, I'm assuming that you read this. So the object's height increases, the speed decreases, such that the object Earth system total mechanical energy remains constant. By how much does the object's kinetic energy decrease in moving from point O, the lowest point, to point P, the highest point? Great. So we can if energy remains constant, right? This is UG plus K, right? And down here is also UG plus K. So the sum of the gravitational potential energy and the kinetic are equal at both parts. So if we go, I think we're going from the bottom to the top, it doesn't really matter. And they want to know how much the kinetic energy changes. So we can hopefully agree that however much the gravitational potential energy changes, kinetic energy will also change. They just change in opposite ways. Yeah, I really need to go to my win block. So how much does it decrease moving from O to P? Okay, so going from this way to this way. So down here, let's call this a height of 0. H equals 0. And up here, this is going to be a height of R plus R. So this is H equals 2R. So our change in GPE is going to be mg, and then our height is 2R. And that's also our change in kinetic. So we're looking for 2 mgr, and that is this last one.